So let us recall our previous discussion. So we introduced magnetic field and what is the requirement to create magnetic field. If we have electric charge, will we have magnetic field around it or not?
If it's static, no. If it's moving, then yes.
Yes. So will we also have electric field, or when it's moving, we don't have electric field?
There is both electrical impulse.
Both fields are there. So what is the difference between electric force and magnetic force?
Electric force can be attracted or repulsive.
The same can be kinetic force in terms of if you consider two magnets, for instance. There's something different there. So if we consider moving electric charge, direction, yeah, to be more specific, how would you describe it?
Electrical force has single direction.
So it acts in the direction, depends on orientation of electric field, of course, but if the electric field is oriented along the velocity vector, it will act either in the direction of velocity vector or opposite, means it will be aligned parallel to the displacement vector. In this case, what we will get? Electric force will produce some work. It will either increase kinetic energy of the charge or reduce. In the contrary, magnetic force is oriented always perpendicular to the velocity vector. To be more specific, it's always perpendicular to the base of two vectors, which is formed by velocity and magnetic field vector. So in that case, no matter how we align our magnetic field, the magnetic force will never be parallel, so it will be actually always perpendicular to the displacement of the charge. If that is the case, by definition, magnetic force cannot perform work, cannot change kinetic energy of the particle. However, it can deflect its trajectory, so that is the feature which can be taken into account and quite widely used in real everyday life. So we considered so far how external magnetic force, external magnetic field exerts some magnetic force on a moving charge. For instance, we considered some example of charge moving in uniform magnetic field. In that case, it starts to move along a circular trajectory because of perpendicular magnetic force, and we have a balance between magnetic force and centripetal force, and that actually gives us centrifugal force if we take into account the directions. And that what happens when we have just a single mobile electric charge. However, what if we consider a segment of a conductor through which there is some electric current flow? So what is electric current? How would you describe it? We did it many times here, but never should be too much to recall it.
Current of charged particles along the line.
Some directional motion of charged particles. Let's say we deal with some metal wires, those are electrons, negatively charged particles, and they are moving in the medium, in the material of this conductor. So that means that we deal with mobile charge carriers. So if we place such a wire in external magnetic field and run some current through the wire, magnetic field will exert certain magnetic force on each of these mobile charges in the conductor. there are plenty of electrons in metals, so each of them will experience certain electric force. And obviously, since we cannot pull them out from the conductors, they kind of constrain in the wire, it will appear that for each length, like each unit length segment of this wire with electric current, there will be exerted a magnetic force from external magnetic field. So our goal now during today's discussion will be to deal with such an example when we have many charges moving inside the conductor, inside some metal wire, for instance, and we want to learn more how to quantify this interaction of a conductor with running electric current with external magnetic field. So let us start with this. Oops. So let us recall what is the expression for magnetic force exerted on a mobile charge. So we can write that it's Q times V d. Well, in general, we can write velocity vector cross product magnetic vector. So if we consider now our charges which are moving in the conductor, then we need to consider so-called drift velocity, means this directional motion of charges in the conductor because of internal electric field, which drives it in certain direction. So in that case, we can write that Fb, magnetic force exerted on a single electron running in a conductor, will be Q times Vd, which is the drift velocity vector, cross product magnetic field vector. And now we need to take into account that there are many charges in this conductor. So that stands for force exerted on a single charge carrier, single electron. So how we take into account all? We need concentration of electrons per unit volume. So we multiply it by n, which stands for a number of electrons per cubic centimeter, meter, whatever units we use. And obviously, we need to take into account the volume of the conductor within which we consider these charge carriers. So this is our conductor. So the length will be L, and here will be area of the cross section A. So here we need to multiply by area and length of the conductor. So that will be total magnetic force exerted on this segment of a conductor with some current I, which is flowing through this conductor. So now let us recall how we introduced several lectures ago the expression for electric current in terms of concentration of charge carriers. Q times N times Vd times A. So this equation should be familiar to you. We considered that a few lectures ago. So now we see that here we have Q, here we have N and A. So we can rearrange this and write that the magnetic force vector exerted on the segment of this conductor with current I will be equal to magnitude of electric current I times L vector times B vector. So in this case, this vector L, capital L, it's a vector which has direction of electric current direction and magnitude of the length of this segment of the semiconductor. So now we have the expression, and if we have a straight segment of a conductor, we can use this equation to determine the magnetic force exerted on it. However, that is some specific case. In general, conductors can be bended in different shapes, and that should be also taken into account. So how we deal with that? So let's say we have some conductor and external magnetic field, B. So here we have some electric current, I, flowing through the conductor. And what we can do, we can just consider a segment of this conductor, like some small element, ds, and represent it also as ds vector. So in this case, dfb exerted on this small segment will be I times ds vector cross product b vector. So now the question is why we consider electric current I here in front of the cross product. Because will it be different if we check any other small element here? No, because they are connected in series. So current, even if the cross section of this conductor is changing, the magnitude of electric current will be the same. So according to the properties of the cross product of two vectors, we can say that magnetic field force will be always perpendicular to both ds and b vectors. And we can actually apply the same rule of left hand in order to determine the orientation of magnetic force exerted on the conductor with some electric current. So in this case, instead of the velocity vector orientation, we will point 4 fingers of left hand along the direction of electric current. Because by definition, direction of electric current is determined as the direction of motion of positive charges. So let us consider some example when we have a current loop and try to understand what will be the net magnetic force exerted on this current loop. So we will have some system of coordinates. So this will be axis x, y, and z. And let me change the color. We will have a semi-circle conductor in the shape of a semicircle. So that will be one part of this conductor. And then will be another part here. So it's a closed loop. Here we will have some current flowing. Let's say we have current I. Obviously, it will flow like this here. So it flows in the counterclock wise direction. So now let us define some dimensions. So we will have here radius of this semicircle, and here will be coordinate of the other side minus r along axis x. Let us assume, bless you, let us assume that it will be conductor number 1, and this will be conductor number 2. So we have two conductors connected between each other, and they form a closed current loop. So now let us figure out what will be the direction of exerted magnetic force on conductor 1 if we place this loop, current loop, in external magnetic field P oriented along axis y, so perpendicularly xz plane. It goes up. So what is the direction of current? It flows along axis x in conductor number 1, this red one. So then we look at the magnetic field vector, align our left hand 4 fingers along the current, then magnetic field vector goes into our palm, and the thumb at the right angle will show us the direction of the magnetic force. So in this case, it will be aligned along axis z. We can write here, and this will be, maybe let's change the color also. No, I didn't change it. It will be FB1. Now, in order to finish this at this point, let us consider what will be the direction of magnetic field, magnetic force exerted on conductor number 2. So this is the direction of electric current through this conductor. So we take this into account, align so that magnetic field goes in the palm, and then the right angle sum will show us the direction of FP2, which will be parallel to FP1, but in the opposite direction. So it will be in the opposite direction of axis Z. So we can show it maybe here. Just to, so this will be FB2. So now we have the directions of magnetic force vectors, and let us determine their magnitudes. So if we look up here, if we want to determine the net magnetic force exerted on some conductor with not straight shape, we want to integrate this expression from point A to point B, which defines beginning and end of the segment of the conductor we are interested in. So the total magnetic force will be equal to electric current, which is the same magnitude, the same along all conductor from point A to point B, and this cross product ds vector times b vector. That assumes that b vector it may be constant or may not be constant. It may change also from point 1 to 2 as we go along the conductor. So that should be taken into account in general. So here we assume that we have uniform magnetic field in which this current loop is consisting two conductors is placed. And let us consider the magnitude of FB1. FB1 vector will be equal to electric current magnitude integral from A to B ds vector cross product B vector. So this is a general expression. And now we need to adjust it to our conditions. So here, the ds vector will be always perpendicular to magnetic field vector, because magnetic field vector is along axis y, and the s vector, when we consider conductor number 1, it's aligned along axis x. So in this case, we can write that it will be I. Range of our integration will be from minus r to r along axis x, and here will be b times dx instead of this cross product, because ds we replace with dx because displacement is along axis x. Then we have right angle between magnetic field and axis x. That will give us sinus 90 degrees will be unity. So we have just b times dx. And here on top of that, we would like to add k unit vector to define the orientation of magnetic force. So we know that this magnetic force FB1 will be aligned along the axis z, means that orientation will be given by k unit vector. So what we can do now, magnetic field is not a function of axis x. So it's constant parameter. So magnetic field is uniform. So we can factor it out from the integral and also this k unit vector. Eventually, we have integral from minus r to r. And here we have dx. So this will give us I times b times k unit vector. And this will be r minus r. Eventually, we will get 2 times I times b times r times k unit vector. And this is our FB1 vector. So magnetic field force exerted on segment number 1 of this current loop. On the segment number 1, this red one, of this current loop created by two segments of the conductors, segment 1 and segment 2. So we figure out with FB1 vector. Now it's time to deal with FB2 vector. So in this case, it's a bit trickier because the orientation of the current with respect to the magnetic field will change as we go from, let's say, point R. We go along this semicircle. The angle between them will change. So let us define ds vector in this case. So this will be some radius r at some angle theta. And if we consider some small segment ds vector here, so this angle here will be d theta. So how do we approach calculation of force FB2? So dF2 vector, which is exerted on this small segment ds vector, will be I times ds vector cross product B vector. So at this point, the angle between ds vector and B vector, we can draw it here. So this angle is theta, and this is ds vector. So we can take that into account and write the following. So it will be I times B times sinus theta. So we have magnitude of electric current, magnitude of magnetic field. We can place maybe here first ds, also magnitude of ds vector, then sinus theta. And we also need to define the orientation. With that, it will be minus k unit vector. So we figure out that FB2 is oriented in the opposite direction to axis z, means its orientation will be defined by minus k unit vector. So that will be true for df dfb2. So now, in order to proceed further, we need to express this ds magnitude, magnitude of the ds vector. So how we do it? Do you recall how we relate the length of a segment of a circle with the angle?
So what? Sector.
Segment of the circle with the angle of the position of the radius vector. So ds is equal to radius times d theta of this. So if we change the position of radius vector by angle d theta, the length which is drawn by the edge of this radius vector, ds, will be given as product of d theta and radius vector length. Keep in mind that d theta we keep in radians in order to have this expression valid, not in degrees. So now we can substitute this expression for ds here in our previous equation and obviously we need to integrate it all over the length of segment number 2. And in this case, how we define the range. So let's write it FB2 vector is equal to minus I times k unit vector integral, here will be b times r times sinus theta d theta IBR sinus theta d theta. And what will be the range of integration? Since we integrate now along the angle theta. Look at our figure. So if we start, for instance, from here and end here. From 0 to pi, exactly. So we go from 0 to pi. So again, we consider uniform magnetic field. Radius also doesn't change because it's semicircle. So we can take them out from the integral. So it will be minus I times B times R times K unit vector integral from 0 to pi sinus theta d theta. This will give us the following. So it will be minus I times B times R K unit vector minus cosinus theta from 0 to pi minus I B R K unit vector will be cosinus pi minus cosinus 0. So here cosinus pi gives us minus unity, cosinus 0 gives us unity, and
Would you say times 2?
minus 2, yes, but we also have here, I guess we forgot this minus and this minus, so they should cancel each other. So we don't have minus here. And this will be actually minus 2I times B times R times K unit vector. So we take a look at this force, which is FB2 vector. And we come back to the previous one, which is FB1 vector. It's the same, just without this sign minus. So now we can write that the net force, magnetic force exerted on the loop of electric current placed in external uniform magnetic field will be equal to the sum of these two vectors, FB1 plus FB2, and this will be equal to 0. So that is actually a general statement, which you need to remember. It's important that no matter what will be the shape of a closed current loop, if it's a closed current loop, regardless of the shape of conductors and segments, different segments of conductors which we use in order to create this closed loop, the net magnetic force exerted on this closed loop will be equal to 0. So obviously, if we consider separate segments, there will be some magnetic force exerted on them when electric current is flowing. However, if we calculate net magnetic force exerted on the loop in general, it will be always equal to 0. So that is the fundamental feature of interaction of external magnetic field with a closed loop current. However, at the same time, regardless the fact that the net force is equal to 0, we should consider another feature, which is actually torque created by this magnetic force. And in case of a closed loop, this torque will not be 0. So that is the feature of interaction between closed loop current and magnetic field, which is extremely widely used in our technology, starting from generating electricity in electric power generators and finishing with electrical actuators. All electrical engines, their work is based on this principle. It doesn't matter that there is no net force exerted on a closed current loop in magnetic field. What matters that this magnetic field creates a torque, and this torque can be transferred to another mechanism, so you can use it as a driving force for rotational motion, and all electrical actuators are based on this principle. So our next topic will be a quantitative analysis of net torque exerted on a closed current loop, which is placed in magnetic field. But I believe we will start that already next time. So now let us summarize our today's discussion. So we consider, instead of a single charge carrier, a flux of charge carriers inside a conductor. Obviously, if we place such conductor in magnetic field, there will be magnetic field force exerted on each charge carrier, and as a result, there will be some resultant magnetic force exerted on a segment of this conductor. So we have shown that what matters, that's the magnitude of electric current, the orientation of the conductor with respect to magnetic field. So here is this, we introduce this vector capital L times V vector. So if we have a conductor with some arbitrary shape, we need to divide it in small pieces, consider small segments, and determine magnetic field force exerted on each segment. Afterwards, we integrate along this conductor. So we have shown on the example of a closed current loop, which consists of two conductors with different shape. So the first one was just a linear conductor, another was semicircle, that when we calculate magnetic force exerted on each of these conductors, first of all, the magnetic forces, they possess equal magnitudes, but opposite direction. So when we sum up and calculate the net magnetic force vector exerted on this closed loop, we end up with a 0. Means there is no net force exerted on the closed loop placed in uniform external magnetic field. And that is the unique feature of the closed loop magnetic field interaction, which you guys need to remember. However, as we discussed already, it doesn't mean that there is 0 torque exerted on this closed loop. And that will be our topic for discussion for next time on Friday. Thank you for your attention and see you next lecture.